Okay, so now we're going to switch gears. In the first three chapters of this course, we talked about some of the we reviewed some topics that we brought up back in Gen Chem 1, and we provided some more information. So now we know a little bit more about liquids and solids. We now know a little bit more about how solutions are made, concentrations, energetics of solutions. And then in the last chapter with kinetics, we started asking some key chemical questions. So in General Chemistry 1 and General Chemistry 2, what we're trying to do is answer three main questions about reactions. And so in Gen Chem 1, we were concerned primarily with what happens. So we were talking about what is a chemical reaction. We talked about stoichiometry. And we talked about acid-base reactions. We talked about precipitation reactions. We talked about redox reactions, all that good stuff. And that was all tied in. Okay. In the last chapter, we talked about how fast does a chemical reaction occur. And so we talked about rates of reactions. In this chapter, we're going to introduce a topic that we're going to talk about for the next 4 chapters. And so that chapter, that question that we're going to talk about now is, to what extent does the chemical reaction occur? Or to what extent does the chemical reaction happen? And so that's the question that we're now going to answer. How do we know? So if we look at this point, we've taken a look at a chemical reaction and we've assumed that it goes all the way to completion. So now what we're going to do is open up that can of worms. Does the reactions go to completion? Well, most of the time, no. And so what we want to do is talk about or find a way for us to quantify how much does this reaction go to completion. Okay. And so with that being said, let's start with a simple system and then think about it in terms of this new way of talking about to what extent does this happen. All right, so let's say we've got a container and we got a container of water. Okay, so here's my liquid. Okay, now above that, we have water molecules. Okay, and I'm going to color those in. All right, so remember, blue dots are water. Now, in air, not only are you going to have water vapor, but you're also going to have oxygen. So I'm going to use this red dot, and I'm just going to randomly put some oxygen up here. Okay, and so remember the red, that's oxygen. Not only do we have oxygen and water, but we also have nitrogen too. So air has a mixture of a lot of different chemicals in it. Okay, nothing terribly new here. Okay, and so the purple represents nitrogen. And so what we want to do, having the water down below, having that liquid, does that ensure, if we remove the air and remove the nitrogen, does that, having that water, does that force that more of the vapor is going to come back and become water? So if we remove the air, so we're going to do this in a vacuum, we're going to see, and this is something that we talked about back in chapter 11 and chapter 12, that you're going to have molecules that are going to have enough energy that's going to pass the water liquid vapor or the water gas vapor and become vapor, but you're also going to have vapor molecules that are going to want to become liquid again. And so this process keeps going back and forth. And the expression that I use for this is that we said that a dynamic equilibrium setup. Okay, where you constantly have molecules go from liquid to gas and then vice versa, gas to liquid, and this constantly happens. We don't really have to do a whole lot for it. It just happens on its own. Okay, so that's kind of what we're looking at. So in the right box, what process will the water liquid undergo? Well, that's vaporization. Okay. And what other process will occur? Condensation, so the opposite of vaporization. Okay. And so how would you describe this process after allowing some time? I'm going to use the word equilibrium. Okay. So at some point, this is going to keep going back and forth. Okay. So if we were to draw some arrows to indicate the movement of this going back and forth, I'm going to use an arrow pointing up and an arrow pointing down, because remember, pointing up goes from liquid to vapor, and then the down arrow is going to be from vapor to liquid. And so the way that we're going to write these is that the arrows are going to be tilted on their side, and we're going to use a double-headed arrow. Each side has one bar pointing in the opposite direction, and that indicates that an equilibrium is taking place. So let's get a definition of what chemical equilibrium is. In chemical equilibrium, the state reacted, this is the state that's reacted, or sorry, the state reached. Let me erase that. So the state reached when the concentrations of reactants and products remain constant over time. Now, this is a working definition. Okay, so this is enough to get us started. We'll expand on this a little bit, but this is I want to stress on you that this is, what this definition is saying. So it's saying that a chemical equilibrium is a state that's reached when the concentrations of the reactants and the products remain constant over time. That doesn't mean that the reaction has stopped. So the reaction is constantly going on. It's just that the concentrations of the reactants and the products are not changing. They're constant. The reaction is still proceeding. Okay, so is this example above an example of static or dynamic equilibrium? We said it was a dynamic equilibrium because it's constantly going. Okay, now one key feature of chemical equilibrium is the fact that the concentrations of the components do not change over time unless you disturb the equilibrium. So going back to our examples, what still continues to occur? Well, even though the concentrations of what's in the vapor and what's in the liquid doesn't change, you still have vaporization occurring. Okay, so you still have molecules going from liquid to gas, and you still have condensation going. So those processes are still going on. It's just that the concentrations are not increasing. Okay, so this concept of chemical equilibrium is very practical in common processes. So let's talk about a couple of them. So the big one is going to be acid-base chemistry. Okay, so we're going to talk about that. This is actually going to be the next couple chapters. So we're going to spend a lot of time talking about how equilibrium is used in acid-base chemistry. We'll also talk about precipitations again. So we're going to go back to precipitation chemistry, and we'll talk about what happens when you have this reaction, when you mix two reactants together and a precipitate falls out. How does that deal with equilibrium? How is that involved? Okay. We can also take a look at another type of equilibrium. This one's going to be more. This is going to be more prevalent. Let's say if you take ammonia, NH3. In order to make NH3, you got to make it from N2 and H2. Okay. Let's take a look at another example of equilibrium. This time, let's take a look at an actual chemical reaction. All right. So we got this picture where you've got three test tubes or three glass tubes, and you've got some chemicals. So inside the one on the left, you have N2O4. Okay. And so what that test tube is being is what that test tube, what's going on is that that test tube is being held into a beaker that's filled with ice water. Okay. And eventually, if you take that glass tube out, like what we're looking at when the second air at the second test tube, the color inside this vessel is changing, so it's becoming more and more darker, and eventually it looks like this red one right here, where that dark red one, that's our product, which is 2 moles of NO2 gas. Okay, so this is our reaction, and this is an equilibrium reaction. So I'm going to put the fancy arrows, the fancy double-headed arrows with the single barbs. Okay. Now, this reaction is actually pretty cool because you can actually monitor the progress of this reaction by measuring the color. So by looking at the color change, you can actually figure out where this reaction is. Is it leaning more towards reactants or is it leaning more towards products? So the darker red color means more product is being made. Darker or the lighter yellow color means that it's going to be more reactant based. And so what we're doing now is to take a look at this graphically. So we're graphing, since we've got two entities that we're dealing with, N2O4, again, this is going to be your reactant, NO2 is your product. And so the reactant has an initial concentration of almost 0.04 molar, and the concentration of the product is at 0. And as we notice, the reaction concentration increases until it levels off at a certain location. Okay. And then same thing with the almost the opposite with N2O4. Initially, the reaction starts losing concentration of N2O4 until it eventually also levels off too. Okay. And so at the point where the concentrations are not changing, okay, and that's why we have this dotted line right here going down the middle. At that point where the concentrations are not changing, that's what we're saying chemical equilibrium is. The concentrations are staying the same. Now, does that mean that the reaction is still producing NO2? Yes, that means the reaction is still going on. Does that mean that the NO2 is breaking down to form or reacting to form N2O4? Yes, that's still happening. So you got a forward reaction going on, you got a reverse reaction going on. Those reactions don't stop. It's just that the concentrations of the reactant and the product stay the same. So every time you make a new product, you're also making another reactant. So that way the concentrations stay the same. Now, if we measure this, let's say that only NO2 is present. Okay. So let's say we start from, instead of starting from going completely from reactant to product, let's say you just got product, you got the NO2. Okay. So the concentration of NO2 is going to be 0.08 molar. And what we're finding out is that the concentration of NO2 is being depleted very quickly because remember, it's a ratio of 2 to 1. Okay. You have 2 moles of NO2 to every 1 mole of N2O4. The concentration of N2O4 is increasing until they both level off. And when the concentrations are not changing, that is chemical equilibrium. So again, the graph on the left-hand side, this is starting from reactant only. And the graph on the right, this is product only. Okay, so that being said, if we summarize what we just talked about, summarize graph A, what we said was that initially we had only N2O4, and then the concentration decreases as the concentration of NO2 increases. But the concentration of NO2 is less than the concentration of N2O4. And so at that point, the concentrations level off. Okay. Now for graph B, you initially only have NO2. Okay. And we see that the concentration decreases pretty quickly, significantly. Okay. So the concentration of NO2 decreases significantly as the concentration of N2O4 increases. Okay, and so what we see is that the concentration of NO2 is going to be less than the concentration of N2O4 as they level off. Okay. Now it looks like the NO2 concentration is the same on both sides. What does this fact reflect? What we're looking at, what we're doing is we're actually controlling a variable. Okay. So considering the start of the process, so if let's take a look at another graph. This time we're going to take a look at the graph of the rates of the reaction. So we're looking at the rate of the forward reaction in blue, and we're looking at the rate of the initial reaction in pink. And so the rate of the initial reaction, of the reverse reaction, is very quickly increasing. The rate of the forward reaction is decreasing until they get to a point where they're both equal. The rate of the forward reaction equals the rate of the reverse reaction. And at that point, that's when we hit chemical equilibrium. All right, so let's go back and answer some of these questions. While remembering the concepts from the last chapter, what can we say about the forward reaction rate? Well, according to this graph, it's going down. So the rate goes down. Okay, and at the start, what can we say about the reverse reaction? The rate's going up. Now, after we wait for stability, which is right over here where it's circled, what can we say about the relative rates? Well, we know that the forward rate is going to be equal to the reverse rate. Okay, and now how general are these conclusions that we're talking about if we start with all reactants and no products? This is a sure bet. This is what we're going to be seeing almost every single time. And that being said, that's enough to get us started in exploring this idea of chemical equilibrium.